In example 310, the book shows an example where they say, where should the zookeeper aim? And they're considering a zookeeper that needs to tranquilize a monkey to do some medical procedure with it, say. And the monkey is initially hanging at a branch, and as soon as the monkey hears the gun, monkeys have great ears, he's going to drop from the tree, same exact second. Now, the zookeeper knows that this is going to happen, and so where should the zookeeper aim? And first I'm going to flip over to a simulation of this. Your intuition might say, I want to shoot below the monkey. And the question is, well, how far below? Is this too low? You can see my projectile went right below the monkey, and so we get a little bit closer. And that doesn't work, and then we get a little bit closer and we still miss the monkey. Now, the solution is to aim directly at the monkey. And the reason why we have to aim directly at the monkey is that both the dart and the monkey are going to fall, or they're going to accelerate at the same rate. They both have an acceleration downward due to gravity, negative 9.8 meters per second squared. Now, the zookeeper is going to shoot the ball upwards, so the dart is going to have some initial velocity in the y direction. The acceleration's in the opposite direction as that. However, we want to aim directly at the monkey because the monkey has the same acceleration downwards. So while the monkey's velocity is going to get larger and larger in the downwards direction, the dart is going to have a smaller and smaller upwards y velocity because the acceleration is in the opposite direction of it. But they are both accelerating downwards at the same rate, and that's why we want to aim directly at the monkey. We've already uniform circular motion. We've already talked about cars that are speeding up or slowing down on a circle, where if a car is speeding up on the circle, it's accelerating. It has an acceleration that some of it points radially towards the center of the circle, and then some of it points tangential to the velocity of the car, and so it has a net acceleration kind of forward towards the ahead of the center of the circle. And similarly, if a car is slowing down, it's going to have an acceleration in the in the direction opposite of the velocity, as well as some component directly towards the center of the circle. What we're going to talk about for this little section right here is uniform circular motion, where the car or object keeps the same speed throughout the entire circle. It's just the direction of the velocity is going to change, and so all of the acceleration is directly towards the center of the circle, or radially. Now we've gone ahead and we've calculated our change in velocity already earlier, where we said v2 minus v1. We did that graphically. We found out the acceleration had to be directly towards the center of the circle. This is called centripetal acceleration when we're talking about uniform circular motion, not centrifugal. Centrifugal is a fictitious force that we'll talk about later, but it's centripetal, and what that is doing is that it's accelerating the object towards the center of the circle, causing the velocity to change not in magnitude but in direction only. Now we can calculate what the magnitude of the acceleration is if we know the radius of the turn and the speed. So the v right there is speed, not velocity, because this is just the magnitude of the acceleration. It doesn't have any direction associated with it. So we can calculate what the magnitude of the acceleration is. also, if we know the period, or the time that it takes an object to go around the circle one full time, t would represent the time that it took for that one full revolution to occur. We could also write the centripetal acceleration as 4 pi squared times the radius times the period squared. If you had a stopwatch and you're timing how long it takes you to, say, swing something over your head uniformly. Not going to talk too much about this, but for non-uniform circular motion, there is going to be an acceleration radially, but there's also going to be an acceleration tangentially, which is in the same direction as the velocity, causing the velocity vector to become larger or smaller with respect to time. In the case I drew right here, it's going to make it larger, and then perhaps over here there is no tangential acceleration, and so it's just going to be, acceleration is all radial, and then the object slows down, still going radially. There was a tangential acceleration in the direction opposite of the velocity, and so on and so forth. The speed of this object is changing as a function of time. That's what makes it non-uniform circular motion. I know it's been a long chapter. We're on the home stretch here. Relative velocity. If you think about it, anytime you observe a velocity, it's relative to you. Therefore, we're going to talk about relative velocity. And a frame of reference is a coordinate system plus a time scale. So I might have a coordinate system x, y, and z, as well as time as I sit here in this office chair. That's my frame of reference. But if I am in my car moving at 10 miles per hour, then my frame of reference is completely different. I'm still going to have an x, y, and z axis as well as a time scale, but now this reference frame is moving along with me at some velocity. Now, relative velocity, if we think about looking at a train, and there is a passenger on this train, and that passenger is walking towards the front of the train, let's just say maybe at a mile per hour. And this train is also moving at 10 miles per hour. So here we are, we're our cyclist, we have our reference frame, we have our x, y, z, as well as time reference. And if we think about it, just logically, you would say if the train's going at 10 miles per hour and the passenger's going at 1 mile per hour, the cyclist is going to see the passenger traveling forward relative to him at 11 miles per hour. Now, the book, of course, has to do this using some complicated diagrams here, and I'll try to walk you through this one. Suppose we wanted to talk about the velocity of the passenger with respect to A, the cyclist. That's what that little slash right here, the velocity of the passenger with respect to A, the cyclist. What we want to do is we want to say that's going to be equal to the velocity of the passenger with respect to the train plus the velocity of the train with respect to the cyclist. I've left off the x. All that really means is in the x direction. So what we kind of knew intuitively is we knew that the passenger with respect to the train was moving at 1 mile per hour, and we knew that the train was moving with respect to the cyclist at 10 miles per hour. And so the velocity of the passenger with respect to the cyclist is going to be 11 miles per hour. And we should also say that's in the positive x direction, just to make sure we're talking about a velocity vector. Now, the passenger's reference frame is going to be different. She's going to see the cyclist moving backwards. And with respect to the train, someone else sitting on the train, they're going to see the lady, the passenger, walking forward towards them at 1 mile per hour. So everyone has different reference frames. Now, we can think of this as we look at an oncoming truck coming out Route 11. I mean, suppose we wanted to know what the velocity of the truck with respect to you was going to be. Well, you would say that's going to be, first, the velocity of the truck with respect to the earth or the ground. Right, the truck is moving at some rate relative to the ground. And then you also need to add in the velocity of the earth with respect to you. Now, the funny thing here is the velocity of the earth with respect to you. What is that? If you look out your window as you're driving down the road, that's going to be equal to negative velocity of you with respect to the earth, because everything is moving backwards. If you're going forward at 60 miles per hour, then the sign that you just passed looks like it's going backwards at 60 miles per hour. So what that's going to be is, what we're going to be left with is velocity of the truck with respect to the earth. Get rid of that. And then that's going to be a minus velocity of u with respect to the earth. And if we just kind of add those together, if here we have the velocity of the truck with respect to the earth, and right up here I'm just going to draw the velocity of u with respect to the earth. And what we want to do is we want to add the negative of that. So that's going to be negative velocity of u with respect to the earth. I'm going to add that to the tip of velocity of the truck with respect to the earth. That's going to be negative velocity of u with respect to the earth. And we're going to get a resultant velocity that's very large. So if you're going at 60 miles per hour north and the truck's going 60 miles per hour south, then it appears to you that the truck is coming at you at 120 miles per hour to the south. Now we can do this in 2 or 3 dimensions. If here we are a cyclist and now the train is moving in that direction and the passenger is now walking in that direction, we can kind of say, alright, 3 meters per second, 1 meter per second. Now we see the passenger walking kind of away from us, and as well as going forward. So this would be the velocity of the passenger with respect to the cyclist. We can do 3 dimensions as well, but that is kind of hard for our minds to wrap their head around, so I'm not going to do 3 dimensions here or even in this classroom. We can also calculate, the angles or the magnitude of this using, say, using trigonometry and the Pythagorean theorem. Now, a real-life application of this is flying in a crosswind. If we consider an airplane that is flying at 200 kilometers per hour to the north, and there is a wind blowing at 100 kilometers per hour to the east, the velocity of the plane with respect to the air is 240 north. The velocity of the air with respect to the earth is 100 kilometers to the east. Then the plane is going to be blown to the east a little bit, and we're left with some velocity of the plane with respect to the earth being blown off course. What an airplane wants to do is they want to tilt over at some angle such that now they're going at 240 kilometers per hour at some angle. That's the velocity of the plane with respect to the air. We have the velocity of the air with respect to the Earth, and now we're left with some velocity of the plane with respect to the Earth traveling due north, which is what the plane, is what the pilot intends on doing initially to reach his or her destination. It's also, we would say, crabbed over in the crosswind. And that's everything we have for Chapter 3.